Good morning, good afternoon, maybe even good evening. My name is Pim, and I'm here to talk you through my bachelor AI thesis named Tracking Dataset Use Across Conference Papers. So really the goal of my thesis was to, given some large corpus of scientific text, construct this bipartite graph that you see here, where you have datasets on the right side and articles on the left. And a dataset node will only be connected to an article node if that dataset is used in that article. And this can be used to extend search functionality of dataset databases to allow users to search according to some particular datasets, or to do some meta-analysis of dataset use across conferences the past years. So this task can really be split into two subtasks, the first being dataset mention extraction. What that entails is really, given some scientific text, extracting the phrases that are dataset referential. So where do we see these datasets being mentioned? This was done using Cybert, and there's a few particular challenges with this subtasks. The first being sparsity. So most phrases in scientific text are not going to contain a dataset mention. So it's kind of like finding a needle in a haystack. Besides this, it's an exploratory task. So that is to say, we have no target list of datasets we're looking for, and instead we have to use lexical, semantic, and contextual cues as to what is or which phrases are referring to a dataset. Next, the second subtask is entity clustering. That's just across all these identified dataset referential phrases, figuring out which ones are referring to the same actual real-life dataset. This is an example of co-reference resolution, for which we developed a custom algorithm using particular assumptions we can make about the nature of dataset names to really improve our performance significantly. So first, let's have a look at Cybert's performance for our named entity recognition task, our dataset mention extraction. There's first two things I want to note. First of all, there's this difference between exact measure and a beginning measure. The difference here is that a extracted dataset mention would only count positively towards the exact measure if the labels match exactly our golden standard, so every word is tagged identically. Whether for the beginning measure, only the beginning of the phrase has to line up. That's really to get a better idea of the performance of our model and how close it is, because of course when we start using this for the downstream task, sometimes we will miss one or two words, but that's okay, because sometimes there's enough information in these first two words to identify what dataset is being mentioned, and therefore for our downstream task our network has done a sufficient job while not attaining to this exact measure. Next, I want to mention that the test set here is zero shot. That is to say that the dataset mentions in the train set and eval set are completely disjoint subset from those in the test set. So not only are different instances of certain datasets, but there are also completely different datasets altogether. So CFAR, for example, will only occur in the train set, eval set, or the test set, but not in both. Furthermore, then looking at the actual numbers here, our network had quite a tight fit of the training data, attaining an exact F1 of 0.93 and a beginning F1 of 0.96, which reflected well onto the eval and test set. However, performance, of course, does drop when we add this zero-shot element to make it a little trickier for our network. But overall, the network has consistently a higher recall than precision, and attain an F1 of 0.84 on our zero-shot test sets. In order to gain a better understanding of our model's performance on this data, the data was split into two disjoint subsets, the easy subset and the hard subset. This split was mainly, or actually exclusively, based on the amount of positively tagged words within a sentence. And an illustrative example is shown here below, where we see the VOC 2007, 2008, and 2009 datasets. This was an example of a difficult sentence, as all these words were tagged to be dataset referential, as here VOC 2007 dataset, VOC 2008 dataset, and the VOC 2009 dataset are mentioned. However, not only is this an example of a summation, so we're mentioning three datasets in a very short span of time, but it's also an ellipsis, where no single element of the summation contains enough information to really understand what's being referred to. It's only when we read the full sentence that we see that the VOC 2007 dataset is being mentioned, the VOC 2008 dataset, and the VOC 2009 dataset. So how does our model deal with this? Well, we see that actually when we train and evaluate on easy versus training and evaluating on hard data, the model's performance does not drop significantly, either in the exact or beginning measure. However, what's interesting is that when we train on the easy data and evaluate on the harder data, performance plummets quite significantly with an F1 of 0.51 as opposed to 0.85. And that makes sense, right? Because it'll see a sentence like this and it won't really know what to do with it. It's never seen sentence structures like this before. However, what's also interesting to note is that our beginning measure, the scores for the beginning measure, don't drop as much. So they only drop to 0.72. And that also means that the model will encounter a sentence such like this, and it'll understand that it's dataset referential, and maybe even begin to label the beginning as a beginning of a dataset mention, a dataset referential phrase, but it won't really know what to do with the rest as it's never seen structures like this before. So that's why we see the beginning measure drop less than the exact. Finally, when we train the model and evaluate it on both, it attains the highest scores, which also makes sense as it will have more training data, and also the patterns it learns on the harder data reflect well onto the easy data. Next, I'll quickly talk you through the entity clustering. So that's the co-reference resolution algorithm that I developed. First, we perform normalization of the dataset names to map them to similar strings and really help our algorithm along. Next, lexical intra-document clustering is performed to form M groups. So we look within each article and look which dataset mentions are co-referential. That's really to help our algorithm in terms of computational complexity, as we will not have to later cluster each or compare each dataset mention with each other dataset mention, but only each M group. Then next, these M groups, so these equivalence classes of co-referential dataset mentions from the same article, are clustered across articles. This is done in 3 spaces. So we actually express their distance in lexical space using character level n-gram TF-IDF vectors, in semantic space using Seibert sentence embeddings. So that's a fixed length representation of the sentence retrieved from the last layer of Seibert, the last hidden layer. And then document level similarity is expressed using Jensen's doc2vec trained on 10,000 conference papers. We then perform linear interpolation of the cosine similarities in these 3 spaces, and that's what you see here, this lambda L. So lambda is for lexical, this is the semantic, and this is the document level space multiplied by their linear interpolation parameters, lambda, sigma, and delta. And element-wise multiplication with this number exclusion matrix is performed. And that's really to make sure that 2 dataset mentions which contain different numbers don't end up in the same cluster, like CFAR 10 and CFAR 100, for example, are extremely lexically similar but should not be in the same cluster. Here we see the results of the grid search I performed across the linear interpolation parameters lambda, sigma, and delta, denoting the importance of lexical information, semantic sentence level information, and document level information, respectively. Below, at the lowest level here, we see the best performing model attaining an F1 of 0.86, a BQ'd F1, it should be said. And that model, or that combination of parameters, I should say, used largely lexical information, a little bit of document level information, and actually no Seibert sentence embeddings at all, which is quite significant to see that these embeddings that we retrieved from the last hidden layer of Seibert are not actually adding any valuable information at all. Next, we see that down here, we use actually solely lexical cues, and the algorithm performs almost as well as it does using a combination of lexical and document level cues, which is significant to see that the model which we developed, or the algorithm that we developed that uses these unique assumptions in order to really improve in performance, could do almost as well using just lexical information as it can combining information from these different sources. So just to conclude here, Seibert was definitely the right choice for the dataset mention extraction task. It was able to attain high scores even with the relatively little training data that we were able to feed it. And that's of course due to the latent space that it learned and identified during pre-training. The custom clustering algorithm was able to attain high scores through making task-specific assumption, but work still needs to be done. So first of all, ellipses need to be parsed better, ellipses and summations, because there's no actual steps being taken to split those when they are retrieved from Seibert and put into our algorithm. They're actually tagged as one entity, and those need to be split in order to be able to properly cluster them. Next, computational complexity is an issue due to the distance-based nature of our algorithm, of our clustering algorithm. We currently have at least a quadratic computational complexity. So that really needs to be addressed. And finally, some end-to-end evaluation has to be performed. Currently, each of the parts, so the dataset mention extraction and the co-reference resolution, were evaluated but there's no real end-to-end evaluation, and no real end-to-end evaluation has been performed. So that needs to be done in order to really understand how well the algorithm and the system will perform in real-life situations. But that's all I have for you. Thank you for listening, and I look forward to your questions.